last day of the workshop and the second day of fully homomorphic encryption and applications. We're very happy to start with Yuriy Polyakov, who's a research scientist at NJIT and at Duality Technologies. Yuriy will tell us about practical lattice-based cryptography in the PALISADE library. Yuriy, take it away.
Thank you, Vinod. And I would also like to thank the organizers for making this workshop happen. I know it's been very challenging. So in this talk, I will focus on state-of-the-art algorithms and latest results from the perspective of PALISADE and from the perspective of their practicality. Some of the algorithms that we'll present here are already published, and I'll just provide references. There are some new results as well that have not been published in papers, but have been incorporated in PALISADE. So these results come from joint work with Andrei Kim from New Jersey Institute of Technology and Antonis Papadimitriou from Duality Technologies. So the high level, so first I want to start with the high level overview, and we will have a couple of introductory slides about the type of lattices that are implemented in PALISADE and which lattice schemes are implemented, just to give a background on the schemes in question. The main part of this talk will be about FHE algorithms, about FHE schemes, and significant focus will be placed on the residue number system representation, double CRT representation, because it's quite relevant for modern schemes, for many popular schemes. The four topics that are highlighted in bold, and that will be the core of the presentations, are BFE RNS variants, and we're going to discuss some new algorithms there as well. Then we're going to present we're going to discuss CKKS RNS variants, and we'll present the new variant that, in our opinion, is quite usable and addresses some of the challenges of RNS variants of CKKS. We will also provide a comparison of BGV and BFV. Some of those results, I think, might not be trivial. We will give a comparison of FEW and TFHE, so based on the recent work with Daniele. Then we will briefly go over some of the multi-party functionalities that we have in PALISADE. Closer to the end of the presentation, we'll give a very quick review of additional capabilities not related to FHE, so what we call Lattice Gadget Toolkit and the protocols based on it. And first, we'll start with basic facts on lattices implemented in PALISADE. And we support cyclotomic rings, and we support Yuriy integer lattices. So those are the two standard, basically, mathematical objects that we support from the lattice perspective. And the ring implementations that are available in PALISADE are all based on power of two cyclotomic rings for various reasons of efficiency and adoption of this in the homomorphic encryption.org standard. However, general cyclotomic rings are also supported, but more at the lower level. We're not using any special capabilities, any new capabilities that they provide to us. Just a side remark, I'm interested in exploring this more in the future, as long as we can get an agreement on how secure general cyclotomic rings are. And all protocols that are implemented in PALISADE are based either on LWE or ring LWE. We do have some constructions based on SIS, but as was shown in previous talks, essentially these problems are equivalent to each other. And one important remark for ring instantiations, we use modulus Q that is either a prime or a product of primes, and these primes satisfy certain constraint that they have to be congruent to 1 mod m, where m is the cyclotomic order in this case, and the main motivation for this is to provide efficient number theory transform capability. So as far as the lattice schemes that are implemented in PALISADE, essentially all 5 schemes that we heard about yesterday, which are the most popular schemes, are implemented. So this includes the BFE. We have 2 RNS variants. This includes BGV, also in RNS, and 2 RNS variants of CKKS. And in this talk, we'll actually talk in detail about one of the RNS variants for CKKS. And then also we have the few and TFHE schemes. So that's an alternative. They can be called as Ducami-Chancha and Chiloti-Gamma-Georgiev-Izopachyan schemes that we'll also discuss in this paper. Maybe I'll give it more of a practicality remark, just a very high level remark on the schemes. And the first 3, BFE, BGV, and CKKS, in my opinion, are very, very practical to the extent that they're currently used in commercial products. I see that as a major advancement for the lattice field, that these 3 schemes are already used basically in commercial applications. I'm extremely interested in the few and TFHE schemes. So they provide certain capabilities that, like related to comparison, for instance, that we do not have with the 3 other schemes. What's the best way to, at least from them, I'll speak from my perspective, what's the best way to integrate them in commercial products? I think is for me, at least, it's still an open question. I see them more as part of hybrid solutions that involve basically one of the 3 core schemes or multiple of the core schemes, and using few and TFHE for certain operations. It's a certainly different, very interesting field, and maybe the main limitation that I see with few and TFHE schemes at the moment is the lack of support of CRT packing. So there is one more scheme that's supported Staley-Steinfeld scheme based on the entry assumption, but it's typically not useful for deep computations. So it's more for historical reasons. In PALISADE, we also support multi-party homomorphic encryption extensions, and specifically one of them is proxy encryption, which has been available in PALISADE since the very beginning, and another threshold FHE approach, which can be a significantly more efficient alternative to multi-key FHE approaches, such as the one we saw yesterday. We have been supporting this functionality and will continue to improve it. I think there is some interesting, there's some interesting applications there. In addition to this FHE-based schemes.
Yuri, there's a question on
Sure.
chat, which is which commercial applications are BFE, BGV, CKKS used in?
So just one second. Let me also, I'm just going to bring up the chat as well. That's okay. So the specifically Duality Technologies has a secure query capability, encrypted SQL-like query, and basically those, for instance, BGV and BFE schemes are used there, and there are also some statistical capabilities that Duality provides that are based in CKKS. So those are the ones that I'm aware of where PALISADE is used for commercial in commercial products. Okay, can I continue? Okay. So so latest schemes, so further other schemes that are implemented in PALISADE. So in addition to FHE-based schemes, we have several schemes based on lattice trapdoors, and starting with the simplest, Gentry-Picard Van digital signature, and ending with certain obfuscation capabilities based on GGH15. So these protocols were developed as part of the DARPA SafeWare program, and well, I think there is some interest in specifically lattice trapdoors and more general lattice trapdoors, and I'll briefly talk about those at the end of this presentation. So one, I would say, major theme of this talk is the use of RNS and double CRT, and it's very important for these 3 schemes, BFE, BGV, and CKKS, that work with large integers. And it's also relevant for other applications based on lattice trapdoors, such as obfuscation or such as key policy attribute-based encryption. And the conventional solution is to use multi-precision arithmetic to support those large integers is typically inefficient. And we all started with this multi-precision arithmetic, except maybe for HELEAP, where Shai and Victor initially started with double CRT, but the original versions of CKKS, of BFE, they were all multi-precision. And we saw that this approach gets very challenging, especially as we increase the size of integers. So now, instead, we use residue number system or Chinese remainder theorem presentation, or sometimes referred to as transfer representation of polynomial coefficients. And we do it for the following reasons. First, RNS works with so-called native, basically, integers, so the ones that fit in the machine word size. And we saw just from the performance perspective that could speed up things up to 10x or so. Also, the nice aspect of RNS is that the runtime scales almost linearly with integer size, which is important as we get into deeper computations. And there are also some hardware benefits, such as, or I would say low-level benefits, such as that RNS dramatically improves memory locality. Computations are easily parallelizable, and RNS supports, of course, efficient hardware implementation. Maybe since we are the two advances we're going to present, very specific to BFE and CKKS, are based on RNS, we want to very briefly explain what double CRT is, what RNS is. So in ring constructions, we typically use number theoretic transform to perform efficient polynomial multiplication. So one of the two CRTs in this double CRT concept refers to the polynomial basically entity. Then the other side, that's the main focus of this talk, is around the representation of large integers. And in this case, we represent a large integer as a product of pairwise coprime native integers, typically of size between 20 and 60 bits. And in addition to being comprime, very often we choose those moduli to actually be the primes satisfying special entity properties. And then these large numbers, or you can think of them as polynomial coefficients, are represented using CRT as residues mod QI. So QIs are the small moduli. And this CRT decomposition, which is often called RNS, so that's what the term RNS refers to, is the second, basically, CRT, the other CRT in the double CRT notion. So this is where that name comes from. So the BFE scheme is especially challenging for RNS, and I'll explain in which regards. And there are certain operations that can be done very efficiently in double CRT directly, and they're actually trivial. They're done independently for each small residue, and these operations include these operations include addition, multiplication, and automorphism. So they're done component-wise. And then there are certain operations that require extra work, and that require estimating the scale, the magnitude of the number. And typically, we do not know the scale of the number when working with RNS residues because they're independent channels. And one of such problems is the scaling that we see in the case of BFE decryption. And the biggest challenge is how to basically apply the scaling by T divided by Q, and T in this case is the plaintext modulus, Q is the ciphertext modulus. How can we do this operation? So the other challenge that we have in the case of BFE is scaling in homomorphic multiplication. There we do a tensor product of two ciphertexts and polynomials without modular reduction, so using effectively double bit width, and then we have to scale this big number by something roughly comparable to Q. And one more operation that actually applies to all three schemes at BGV, BFE, and CKKS is the you can think of it as digit decomposition or gadget decomposition. It's the high-level idea is that we need to take one of the polynomials and decompose it into digits, and that's in the classical formulation that requires going back to multi-precision representation. So to address these concerns, two RNS variants of BFV have been proposed and actually implemented. Both of these, the optimized versions of both of these are currently implemented in PALISADE. So the first one is the BEHZ variant that is based only on integer arithmetic, and internally it uses small Montgomery reduction and some auxiliary moduli. And the other approach, the HPS variant, uses both integer and floating point arithmetic. And the main differences in the RNS procedures, the main differences between those two variants are in the RNS procedures used for decryption and multiplication. The digit decomposition is solved the same way that was originally proposed in the BEHZ work. And so until very, very recently, it was believed that the HPS variant has a certain practical limitation, that it needs to use extended floating point precision, such as long doubles or quad floats, to support moduli that are larger than 45 bits with, let's say, up to 60 or 64 bits available for native operations. And the other result was that that the BEHZ variant may have a higher noise growth, as was observed in one of the previous papers. And actually, we're going to present some results showing that both of those are no longer true. So the HPS RNS variant, the high-level idea, in my opinion, is relatively simple. So we'll look at the actual CRT representation of a large number, so large integer x in this case. And we just basically write the regular CRT reconstruction as we're used to. The only, I would say, challenging part is that when we do not apply mod q to this expression, we have a certain number of overflows of q as when we compute the sum. And this number of overflows is represented using this nu or nu prime, depending on the formulation of the CRT reconstruction. And actually, that nu is basically somewhat of a challenge when we talk about some RNS procedures. So the high-level idea of specifically the HPS variant is to write down all those expressions, substitute those expressions when we need them, and then decompose the results into integer and floating point parts and do some basically tricks there. So let's see how we apply those to the scaling and decryption.
Yuriy, a question.
Sure.
Where are the floating points in this formula? It sounds like sort of everything is an integer, at least the second formula. Oh,
yes. Yes. So far, everything is an integer, and both RNS variants that I mentioned basically start from these formulas. We introduce floating point arithmetic for intermediate computations. So the idea is we can do some floating point tricks, but for intermediate computations, we always go back to the integers after that to simplify, to develop relatively simple algorithms.
Can you give an example of what an intermediate computation is?
You'll see it in just this slide.
Oh,
okay, so so this is going to be a good example. So scaling and decryption. So in this case, let's think of x that x represents a coefficient of a polynomial in the that we get as a result of the decryption of operations, for instance, C0 plus C1s in the case of these three schemes. So it's just a representative coefficient. So we substitute one of the CRT expressions in this case, and it can be easily shown that this part basically is eliminated automatically because it's going to be a multiple of t with the plaintext modulus, so we can immediately discard this part. And the part that's left is only the first term, and after just applying basic simplifications, we get to this expression. And this is where we use the floating point tricks in the decryption operation. We represent this with basically the expression in parentheses as we split it into integer part and floating point part. So the integer part essentially is the result of the floor division. You can think of it extracting that way, and then the rest is that's related to the remainder of what we get is represented as a floating point number. So theta I is in this case a floating point number that we use, and after. So effectively, that's how we perform the computation, which was just written here. Is we substitute these numbers, we do certain precomputations that at the precomputation stage we use some larger numbers, but during the main computation of decryption we don't. And we're able to avoid the use of any multi-precision arithmetic in the main computation. And there is a challenge though that the challenge is related to the approximation error accumulating from rounding, from performing the part that deals with the floating point part. Maybe just before I get into, explaining this further, did this answer your question? Because this is just one example.
Yeah.
Okay, and there will be another example afterwards. So it's like we can do certain things using floating point arithmetic that inherently are dealing with multi-precision arithmetic, but of course some error can be accumulated, but we find ways to either make this error go away or it becomes not relevant, or because the noise is higher. When we deal with this floating point computations, we get a certain error, and in this case, the error term, xi, basically sum of xi multiplied by epsilon I, has to be less than 1 divided by 4 to basically to preserve the correctness of decryption. And just for the case of doubles, we can restrict this epsilon I to something to the power of minus 52, just since that's natively available. And if we restrict the k, which is how many small moduli we use in the large modulus, to 32, then the highest modulus bit size that we can support with doubles is 45. And if we need something higher, and 60-bit moduli are preferred, for instance, in BFE implementations, we need to use either long doubles or further quad floats. So the first new algorithm presented in this talk is sure.
Can you go back one slide?
Sure.
So what is epsilon I? Is it theta I scaled by q? Qi?
Just like which one you're epsilon I? You're asking about epsilon I?
What is
epsilon I is the double float, basically the error of double, simply speaking. So whenever we perform any computations with doubles, we achieve, let's say, 52 bits of precision. So this is any error that we accumulate from basically doubles there.
I see. And the xi's, they're not necessarily, they're not bits, right? Each xi is at most qi.
That is correct. So imagine, desired scenario would be QIs roughly 60 bits, or 62 bits, depending on basically implementation, and we would have a 60-bit number multiplied by this error, and you can see that this sum can become very high and much larger than 1 divided by 4.
Sure, right.
Okay, so the new algorithm we're presenting in this talk, and it's currently implemented in PALISADE, is how to eliminate this problem of using quad floats or long doubles. And actually, the idea, Vinod, comes from your earlier work on digit decomposition and just the standard HE trick that's used in key switching. Hopefully, BV11 is the first work that mentioned it, but that's to the best of my knowledge. And we simply decompose xi's into digits. I mean, in this case, it's sufficient to use 2 digits. high and low. And we introduce the digit size of basically R bits in this case. And we write down this expression. Basically, we split into digits and we independently do some pre-computations for the low digit and for the high digit. Essentially the same idea. The high-level goal is to reduce the magnitude of xi, which would be 60 bits in the previous case, to something, let's say, like 30 bits in this case, if we split it into. So that's the high-level idea. And so it's after this, during decryption, we have to compute slightly more. It looks like slightly more. In reality, it's comparable to what we previously had. And yes, I think it went a little bit too fast. So the error in this case is, the approximation error that we get is basically sum of two errors, and the main difference is that xi low or xi high is basically up to 30 bits in this case, and it's very clear that this sum will be substantially less than 1/4 for any reasonable choice of moduli that we can support. So something that worth noting, although we increase the number of operations in this case, in most practical scenarios, we actually eliminate any modular reductions because these numbers are small, such as xi. We can perform all operations without any modular reduction, so it's plain multiplications and additions. So this is, so in terms of performance, the basic performance is very comparable to the approach without using digit decomposition, even for smaller moduli. And maybe a side note, just like some other RNS procedures proposed in the HPS work, this is a general trick. So it's first of all, we can generalize it to any number of digits if needed for a given application, if our goal is to reduce a floating point approximation error. Whenever we can think of it this way, so whenever we have a problem where we're working with floating points as an intermediate step in some mode to support modular integer computations, we can always use that trick to reduce the precision for floating point computations. So from the practical perspective, this removed the requirement in PALISADE for any basically extended precision floating point numbers.
There is a hand raised in the chat.
Okay.
You see that?
Let me see. So in the chat, let me just, it's a little bit, I see Q&A. Let me try to access the chat just a sec, because I don't see the chat window, sorry. Okay. Maybe a person can ask a question. So let me see. Mm-hmm.
So Daniela, it's I think hand has been raised for a while. So let's.
Oh, it's just a false positive. Okay, fine. Ignore it. Sorry.
Okay. Yeah, and I'm actually just brought up the chat as well. Okay. So I'm going to continue. So one more step. So this is not new. But I still wanted to present it for completeness. So the CRT-based extension, another major problem that was addressed in the HPS paper, also directly works with one of the reconstructions that we discussed. So let's say we want to extend to modulus P. We write it down, the reconstruction itself with modulo P. And the biggest challenge that we have in this situation is in estimating the value of this nu, because that's the number, it's an integer that represents the number of overflows. And in this particular scenario, basically, the value of nu can be easily shown. Basically, it can be computed using this expression. And in the computation itself, we use, again, both integer and floating point numbers. But this is another case where floating point numbers come up. And in the CRT basis extension, the biggest challenge is the this estimating new. As soon as we know new, then the rest can be easily computed by using integer arithmetic. In this case, for estimating new, we can use some intermediate floating point steps. I mean, the details are not mentioned here for conciseness, but they're presented in the paper. And the approximation error introduced, I mean, from the practical perspective, in the case of homomorphic multiplication, is basically essentially negligible. So something that I wanted to show, so this is, I wanted to show just how fast is BFV these results are somewhat faster than what was presented in the HPS paper, but probably by 2x to 3x, depending on the specific row. Maybe the main one, there are two, I think, interesting observations from this table. So the first observation that even when we go to the, let's say, so L in this case represents the number of levels, the effective depth of the computation, N is the ring dimension, log Q, of course, is how many bits we have in the ciphertext modules, and K is the number of small primes. So we can see that even in the case of depth 50, or I mean, well, I would say let's start with depth 20, we are getting some very reasonable numbers under 100 milliseconds, which means we can support relatively deep computations, level computation in BFV. We can even support computations that are basically much larger than that, but at that point, bootstrapping is probably will become something that can speed up the computations. The other aspect that I would like to highlight is because we're going to come back to it when talking about BGV versus BFV, is the cost of multiplication. So we listed here 3 primitive operations: addition, multiplication, and rotation. The multiplication in the case of BFV involves some relatively heavy, basically, operations related to this tensor product. And then it's followed by key switching. Rotation is pure key switching. And in the case of BFV, we can see that the effect, the cost of actual multiplication before key switching is higher than is the cost of key switching. And they only get comparable to each other at basically the depth of 50. So something to take away that BFV has an expensive homomorphic multiplication, because we often look at key switching as being with a bottleneck. It is not in this case. So just to maybe a practicality remark, and I think I've already answered this question, but what do these numbers mean? I mean, and concretely, they mean that this BFV implementation is used now in a commercial product of Duality that does encrypted SQL queries. So what I'm saying is that the numbers we're seeing here are really practical to the extent that this technology can be commercialized.
Sorry, Yuri. So you said that multiplication is the expensive operation, and what makes it expensive? You said it's not the key switching; it is the product part. And
it's the tensor product. So we have to multiply 2 ciphertext without modular reduction. So we have to do CRT basis, which have to extend the basis, the RMS basis, which involves a lot of entities. We have to do the multiplication this basically with a double bit width, and then we have to scale it down. And all of this requires a number of entities that is comparable even to like the slowest key switching operation.
So it is the entities what carries most
entity
of the cost.
Inside that, yes. Entities, not the RNS procedures. Yes, maybe to your question. Yeah. Mm-hmm.
Yeah. Thanks.
Okay, so let me just to wrap up this part.
Yuri, there's a clarification question, which is depth L the number of multiplications, or depth as in the number of multiplications?
So very often in these schemes in BGV, BFV, CKKS, we use the binary tree technique, which basically we're referring to the depth of the binary tree. So it's, I mean, basically closer to the second. So 2 to the power of basically L is the number of multiplications in a chain that we can perform. Mm-hmm. So some notes on how do the HPS and BEHZ variants compare based on the state of the art? So thanks to Vincent Zuka and Ahmad Al-Badawi, PALISADE has a very efficient implementation of the BEHZ variant. So we can compare how basically they run. And for the sake of conciseness of this presentation, I did not present the tables, but the high-level results of the comparison are the following. The runtimes of those two approaches are very, very similar. I mean, almost the same. And the main bottleneck is in the number of entities, and the number of entities is roughly the same for both approaches. So this is, after all, state-of-the-art optimizations applied to both variants. The noise growth is actually the same in both variants. So this was noted recently, basically in the paper that I mentioned. And all those improvements were added to PALISADE and implemented. So from the noise growth perspective, these are basically also equivalent to each other. There is only one, in my opinion, significant difference. It's a usability difference, which, and we'll talk more about usability during this talk later, is the fact that the HPS variant is much simpler. And I was essentially able to explain most of the ideas in 5 or 6 slides, while the approach based on Montgomery reduction and so on is certainly much more challenging to understand and implement. But in terms of runtime and noise growth, they're essentially equivalent. And just the implementation side note, the RNS procedures from both variants can be mixed as needed. So it's one does not have to restrict basically to one variant or the other. They can be mixed as needed. So the next topic is going to be CKKS. So if there are any questions at the moment related to BFV, I'm happy to answer those. If not, I'm going to go to the next part. Okay. So we'll focus. So we had a nice presentation yesterday from Young-Soo about CKKS. And so in this part of the talk, we're going to focus on the challenges of RNS variants of CKKS, and also usability challenges and in general of CKKS. And we're going to present some ideas that improve those. So a big challenge in the RNS variants of CKKS is modulus switching. So modulus switching is not new. It was used in BGV, for instance, to control the noise. Here, it has a slightly different meaning. So in CKKS rescaling, so we call delta is the rescaling factor. This ratio, Q uppercase to Q lowercase, corresponds to the scaling factor that's used in encoding certain, let's say, floating point data. So it actually is meaningful. It has a certain meaning of the scale of the message. And in the original multi-precision CKKS, I mean, I'll quote, I think, the textbook CKKS in a couple of places. This delta is typically a power of 2, which is very convenient for many reasons. And both uppercase Q and lowercase q are power of 2. In RNS variants of HE scheme, since we have to perform the number theoretic transform efficiently, that's our goal. These two moduli are decomposed into products of small primes, and typically this lowercase q divides uppercase q. And the operation of rescaling in CKKS requires scaling down by this delta, basically to the power of p. But we cannot use, given the constraints that we have for basically for lowercase q and uppercase q, we cannot choose something that's exactly matches to the power of p. And the best we can do is to find a small prime that is close to the power of p. And based on this idea, so
Yuriy, just a comment. Excuse me, that's shy. There is a sort of theoretically easy solution, and we actually implemented it in NJIT a while ago. You don't have to just scale by a single prime. You can multiply by one prime and divide by another, right? So you can have, if you want to drop it down by just 2 bits, for example, you can multiply it by a prime of 40 bits and then divide it by a prime of 42 bits, and you'll get the same result. It's a little more expensive while you do the operation, but it actually lets you do any kind of fine-grained precision that you need in the computation. And in many computation, it's worth doing that.
Mm-hmm. Yeah, thank you for this remark, Shai. And I think it might be a good idea to come back to more detailed discussion, because I'm going to present a slightly different way of handling this problem. And maybe we could have, I mean, it would be interesting to actually compare the approaches and what we get from them. So thank you for the remark. We'll certainly get back to it. So in the initial CKKS RNS variants, and essentially the one that was implemented in Heian RNS and the one that was implemented in PALISADE a while back, this approximation was treated as an extra noise. And in HELEAP, it was handled a little bit different, and we'll come back to it a little bit later. And the RNS moduli QI are chosen such that 2 to the power of p divided by QI stays in the range of 1 minus 2 to the power of minus epsilon to 1 plus 2 minus epsilon, where 2 minus epsilon is kept as small as possible. So basically, this epsilon is used as a metric of how many basically bits we're basically paying for the approximation. And maybe a simpler way to look at it, when we perform the first multiplication and rescale operation, our effective scaling factor changes from the initial factor of 2 to the power of p. It changes to 2 to the power of 2p as a result of multiplication, and then divided by QL, where L is in this case just the last modulus. So we're doing from the very start. And we divided by that as part of rescaling. So effectively, the rescaling factor changes from 2p to 2 to the power of 2p divided by QL. And it's simple to show using this kind of notation that we introduce an approximation error of roughly p minus epsilon bits. And the idea that at least was used in PALISADE in the approximate variant, and I would imagine similar idea was used in the RNS variant of Heian, is to alternate the moduli around to p to minimize the error. So there is some cancellation of error, but not perfect cancellation, because we're dealing with primes with certain constraints. Still, the error keeps growing as we increase the ring dimension and depth of computation. And in those scenarios, we've observed that the rescaling approximation essentially dominates over the CKKS noise. We can even disregard the CKKS noise and estimate the approximation, the error, based on just rescaling itself. And the question we posed, can we avoid this approximation error? And so I'm going to get into the discussion of an alternative RNS variant that's available in PALISADE. Actually, I think it's available since November, but we haven't had a chance to write it up anywhere. So this is joint work with Antonius Papadimitriou. And the question, the answer to the question of can we do better? I mean, Shai already said we can do better, but we'll take a slightly different path in this case. Yes, we can eliminate the approximation error, but the cost can be too high. So the rescaling error is deterministic and depends only on 2p and the modular QIs that are involved in this. So we can always adjust the scaling factor by certain extra multiplication. So a naive solution would be to do this adjustment to multiply by a scaling factor after every multiplication. And we can basically preserve, let's say, the original scaling factor of 2p by carefully choosing the adjustment factors. But the challenge here, essentially, we're introducing one extra level. So we have to do one more scaling multiplication followed by another rescale. So conceptually speaking, this naive solution would double the number of levels and make this approach highly inefficient compared to the approximate one. Can we do better than this? And this is the question we were trying to answer with Antonius. We'll walk through several challenges that we ran into while answering this question. So the first challenge, how can we efficiently adjust the scaling factors, minimizing the performance cost? I mean, in other words, we do not want to use a naive solution, we want to do something better. And the answer to this question is, if we use the natural or order of CKKS, and natural meaning we start with a certain scaling factor, and then we just compute the scaling factors for further levels by implying multiplication and division by the basically current prime modulus. That's what we call the natural order. we can avoid many of those scalar multiplications, and we would only need to perform scalar multiplications in situations when we deal with ciphertext at different levels. Only in that case, we would have to basically adjust them. But the important part is each level has a different scaling factor, not the same scaling factor of 2 to the power of p as an approximate variant. And there is one minor optimization we applied here to eliminate some extra scaling. We could choose the first modules to be QL, not 2 to the power of p in this case. Okay, so we have a solution that's more efficient, but now we're introducing this relatively complex logic, let's say when we want to add two ciphertexts together that are currently at different levels. And how can we hide the scaling factor adjustments from the users? Basically, how can we do them automatically? Because we don't want to expose another complication to the user. And our solution for this problem was that first we keep track of the scaling factors for each level, so we can, easily multiply by the appropriate scaling factor when needed. We automatically adjust the scaling factor when needed, so it's an automate, so it's a library capability, not something that the user has to think about. And we also want to automatically rescale. And this is necessary for this variant to enforce the natural order of scaling factors. Otherwise, there would be many combinations of scaling factors. So automated rescaling is something that's certainly very useful for this approach. So challenge number 3. Okay, so now we got to automated rescaling, which obviously is a problem by itself. Vinod, you have a question?
Yeah. So the scaling factor is dictated by the underlying computation, right? It says, when you multiply, how many bits do I drop? Isn't that right?
Yes. So there are different. So I would say there are different high-level approaches to this problem. So one way is to use a granular metric, and that allows you to, for example, minimize the size of Q that you can use, and I believe that's what is done in HLib. The other approach is more, I would say, simplified, is that you work with the same scaling factor throughout the computation, roughly the same. I mean, in this case, we still maintain that, and you assume that basically this level of, like, let's call it similar to 32-bit or 64-bit native type, that there won't be any basically overflows of this particular size is sufficient. So it's maybe like pushing the problem a little bit, like in oversimplifying it, but being more conservative in allowing more bits. That's how I would probably classify it.
Also, Vinod, I mean, if you think about it from a point of view of somebody wanting to use the CKKS, they don't particularly care about scaling factors. I mean, what they know is, their inputs, maybe something about the size of intermediates and the type of outputs that you want, and the accuracy that they want. They don't care how much you scale intermediate computations there.
Okay, I see. So you're saying, the ways to adjust these scaling factors that are more crypto friendly will have sort of accuracy implications, but that's something to sort of, something to experiment.
Yes. So this is, I would actually support what Shai said yesterday during Young-Su's talk, that yes, this rescaling, this, all these challenges with CKKS is a problem, but it should be a problem for us. I mean, for, let's say, in this case, I'll refer to myself as a library developer. We should not make it a problem of the user. We should use some automated logic that basically hides this. And that's the approach that's used here as well. So this is, we're looking from the perspective how to make it usable, and that's maybe partially motivation. And we don't want to expose that native complexity of CKKS. Okay, maybe I'll continue just.
One more sort of point. So you're saying, one should sort of come up with these parameters, these scaling factors, right? And then one should, you really want to know what effect this has on the accuracy of the final model, or so the convergence time or whatever. So this, you're saying, do a plain text, fix these parameters, and then one can do plain text experiments on maybe a small subset of data or something to figure out.
Exactly.
All right, thanks.
and that basically, I mean, if you have a certain model for the CKKS scheme, you can run those computations, and you can, or you can even come up with some theoretical estimates, but they're much harder to derive. So that's the idea. Given this basically scaling factor, what can you get at the end for a certain computation?
So sorry, Yuri, this is Hao. Can I ask another question on the previous slide?
Sure. Maybe would it be possible for me to finish with just describing the algorithm here, and then I'm happy to answer all those questions, just so we at least finish the CKKS part.
Okay, let me know when I should ask.
Sure. I'll actually, just to. Okay, so what logic should we use for automated rescaling? Because obviously that's by itself a problem for even the textbook CKKS. And what we chose as the solution is to do the rescale automatically right before the next multiplication. So we're not going, so let's say we have one multiplication followed by certain operations, let's say rotations or additions or something else, and then a little bit later, we do another multiplication. So for the automated rescaling, we chose the option of doing the rescale right before that basically following multiplication. And the motivation for this is that we perform all computations between these two multiplications using the noise budget that we get from the prior multiplication. And what this means that many intermediate operations become almost noise-free. I mean, this is a big challenge, for example, for rotations in certain key switching techniques such as BV key switching. So we're able to at least kind of like assimilate that noise that comes from those intermediate computations into the noise budget of the previous multiplication. And there is a minor cost in performance for this, because effectively we're not going to rescale immediately, but we're going to keep one more prime, basically, that typically gets dropped as part of rescaling until the very end, until we need the next multiplication. But to be honest, that cost is not very significant, because I mean, when we especially work with a large number of primes. So then there was another challenge. And so with these scaling factors that are different for each level, we noticed that after performing a certain, because the scaling factor computation means squaring and division every time for every level. After a certain relatively small number of levels, sometimes 15, 20, we observe how the scaling factors diverge either in the direction of 0 or infinity. In other words, at a certain point, they become useless to us. While we may not care about the exact value of the scaling factor, we want to stay within at least 1 bit of the original, I mean, like, let's say, scaling 2 to the power of p factor. So our solution for this was to choose this small primes qi in a way that the difference between the scaling factors for each level are minimal. So so the procedure that is presented here, I'm not going to go in all the details, but the idea is we start with a certain scaling factor, like QL in this case, and then we choose all other prime moduli for the following levels in a way that minimizes the, I'll call it the error, or basically in choosing the next scaling factor. So that the scaling factors stay as close to each other as possible for basically many levels. And from the practical perspective, we ran, I mean, we didn't do any theoretical estimates yet, but from the practical perspective, for something like 2 to the power of 16, we saw that this variant could still support, let's say, 80, 90 levels without any problems. Obviously, for smaller ring dimensions, this would be, the number of levels is higher. So for all practical reasons, this would be sufficient. So I'll try to fast pace this a little bit, just so we could, I could answer some questions related to CKKS. So the high-level story is this: the rescaling error in the exact RNS variant is basically very similar to the error in the textbook CKKS. So at least we solved that problem. And the net effect that we get output precision, which is very similar to textbook CKKS precision. Then the other problem we had to solve, but it's very useful from the usability perspective is that rescaling and modular switching, but here I'm referring to the modular switching used in the original CKKS paper, so level reduction without changing the scale, in this variant are done automatically. So in other words, any adjustment of scaling factors, rescaling, modular switching, they're all done automatically. The user does not see them. The user does never calls rescale directly. Of course, there is a certain cost, but our goal was to minimize that performance cost. And depending on the computation, the difference in speed that we saw between the approximate RNS variant and the exact RNS variant it ranges between 1.1x to 1.5x. So it's I would say it's not dramatic. It's in my opinion, it's a reasonable cost for a much simpler version of CKKS, and we get a much higher precision. So yeah, this is a good topic so I can answer some questions now related to the CKKS.
So Yuriy, could you go back to the slide about the different scaling factors per level? This is how. Yeah, this one. So I was just wondering because in some cases you could end up with ciphertext on the same level, but they still have different scaling factors, right? So it depends on the order of operations you do to arrive at that level. So
that's why automatic rescaling is introduced.
Okay, so if such
we control how rescaling is done. That's how we solve the problem.
Could you give a little bit more detail about how you control it?
That was actually in the slides right after this. I mean, I'm happy to repeat it, but this is exactly what I was discussing, how we actually do automatic rescaling. So how, maybe for the sake of time, is it okay if I just continue, and then I'm happy to explain this in more detail offline. Sure.
Yuriy, there are two questions in.
Sure.
There should be quick questions. Read it out.
Yeah. So the first question, instead of using the original delta as the scaling factor, we use different factors for each level. That is absolutely correct. I mean, that's what we're doing, and we're doing it essentially to preserve the natural order. And I mean, the scaling factor itself doesn't matter too much as long as we keep basically work with the same number of bits, but we want to basically eliminate or minimize the error that's introduced. So is there still a way to manually manage the rescale? So yeah, this is a good question of optimization. So in the approximate version, of course, we provide the ability for the user to manually rescale. In the exact version, it gets a little bit trickier because one could break that logic of how the scaling factors are chosen. So that's why we so we use the approach that we take care of the rescaling to minimize the situations when there is an issue due to optimizations. Okay, I'll try to very quickly go through a couple of slides because it looks like time-wise we're running out. Just there are some other interesting results to share, but very briefly. So key switching in CKKS and BGV. So Yangsu briefly touched that. There are several different key switching techniques that can be used, and all of them are actually implemented in PALISADE. This is more of a guideline, just based on our current understanding, basically the state-of-the-art choices for key switching, basically for the RNS decomposition or for key switching in RNS that is specific to CKKS and BGV. Basically there are two methods that are most relevant. So when the number of levels is relatively small, and we typically the so-called DV, digit decomposition, but the RNS version of it is the fastest. The only basically gotcha there is that it may introduce some significant noise when doing rotations. There is a workaround for that too, but that's the only consideration. When we get into deeper computation, the best key switching technique that's available is essentially what's called as hybrid key switching, and it's a combination of the basically JHS key switching with RNS decomposition. It's much faster for deeper computations for sure. It does introduce some auxiliary moduli, so the requirements from the LW perspective are a little bit different. But it does not have the noise issues that the BV that basically the BV key switching has. From the performance perspective, this is not a big issue for BFE because multiplication is often costlier than key switching, but it can be an issue when basically dealing with noise. So this is, in my opinion, an interesting result. I think it's relatively trivial for basically when you have those both BGV and BFE available. So this particular table compares the runtimes for BGV and BFE in PALISADE, both RNS variants, for a computation that is a chain of basically 2 to the power of def minus 1 homomorphic multiplications. So it's like a binary tree multiplication in this case. This was, of course, this is a very special computation that was chosen to highlight the advantages of BGV, but maybe to give some thought. The fact that homomorphic multiplication is expensive in BFV makes BGV a better, from the efficiency perspective, option when basically, when a lot of homomorphic multiplications are involved. And the extent to which this is true, so we look here at depths from 2 to 6, and 6 essentially corresponds to a large number of multiplications. We have a speed up ranging from 1.3x to, I would say carefully, to 5x, basically, because I think that very first choice is probably very special. But there is a performance increase using BGV in RNS for the computations that involve homomorphic multiplications.
Yuriy, question, do you have any kind of results for really deep circuits, depth 40, 80?
Probably the computation would have to be different. I did not run them, but it's very so I think the trend can be seen from this table. As we increase the depth, the effect becomes less significant because the key switching starts dominating more and more, and actually what we saw in the BFE table previously. So I would say it's going to get the ratio is going to get basically closer, to 1, and at some point even BFE might be more beneficial. But I did not run those experiments, but that's kind of so it's a very good remark that for deeper computations the result might differ.
Yuriy, I wanted to ask pretty much the same question, and the question being, what is the crossover point? It'd be interesting to sort of figure it out.
Let's call it an open question. I did not run exhaustive computations yet. Let's call it open, but it's an interesting question, and in my opinion, both schemes are very useful, in practice. And of course, the complexity that they're used. So very briefly, this is the major result, and other things is just pointers to the previous publications on PALISADE implementation. So I'll focus on this major result, and I think we can stop at that. So Few versus TFHE. So very recently, Danielle and myself examined both schemes and tried to compare the schemes and understand the differences between them. And there is a paper on this in April, but I'll just highlight the main findings. So when instantiated using LW and ring LW, both schemes are essentially the same, except for the bootstrapping procedure. So in other words, the use of torus is not necessary. That's a convenient encoding basic technique. But in terms of the basically underlying algorithms, the main difference is in the bootstrapping technique. Of course, there were other optimizations that were applied later in the TFHE papers and some enhancements such as circuit bootstrapping. Our analysis shows that all of those techniques can be equally applied to Few and TFHE. So that's so in other words, it's the same family. It's very similar. Even one could combine two bootstrapping procedures if needed. Then another, in my opinion, important result of this paper it shows that although the original TFHE scheme was explicitly formulated for binary secret distributions, and which are still kind of being discussed at this point, how, I mean, whether they basically whether binary secrets are considered very secure. The scheme itself is not limited to that choice. So we show that how it can be extended to ternary or Gaussian secrets. And in terms of its behavior with different secrets, we show the trade-off showing, and on the x-axis we're looking at different secret key distributions, starting from binary going up to the Gaussian theoretical. And it's interesting to note that runtime-wise, the few and the TFHE cross at basically a ternary distribution, ternary secret distribution. So there are just two different options shown here for a few, depending on the digit site that's chosen. Then afterwards, the few, which is based on AP-based bootstrapping, becomes actually faster. But there is another side, is the bootstrapping key size, and the bootstrapping procedure, the Jinx bootstrapping procedure using TFHE, has major advantages over that. We can see that if the bootstrapping size is a concern, then the TFHE would be preferred, the Jinx approach would be preferred. In the case of Gaussian secrets, or both practical or theoretical, the distinction is really not clear. Depends on whether runtime is the main metric or the size is the main metric. So there are more results, but I would say the other results are published, and I'm happy to share the slides. I'll just very quick, because of the time.
But you're 9 minutes over, so maybe it's good to sort of wrap up.
Yep, absolutely. Yep. So very brief, I'll just go through those, that there are some protocols related to Lattice gadgets, and information about PALISADE, and I'll share the slides. Then, yeah, thank you. Okay, so the question, so I'll try to, so it's 40, 12, okay. So that's PALISADE.
Yuriy, 1 second. So let's actually thank Yuriy, and Yuriy will take the questions in the next sort of 5 or so minutes, and we'll reconvene in about 5-ish minutes with Peter Scholl.
Thank you. Yeah, I'll try to be very quick. So does PALISADE implement bootstrapping for CKKS? The public version of PALISADE does not currently have bootstrapping for CKKS. The plan is being discussed. Is gate bootstrapping in PALISADE faster than TFHE leap? No, it's not. The implementation in the PALISADE does not use AVX extensions. Basically, we try to stay as generic as possible. But if AVX extensions are used, then all estimates show that the runtimes are going to be roughly the same. Let's say for the binary secret. Then for the practical commercial applications for the PALISADE library, how large for the database that can be supported, what type of queries that can be performed? Yeah, I think it's hard to answer this question in a very concise manner. I would rather take it offline, and please send me an email, and I'm happy to give a better explanation of this. What is the proxy re-encryption technique implemented in PALISADE? So the idea is that we can leverage key switching, the same key switching technique that was discussed in the context of BGV and CKKS, to switch from one key to another in a publisher-subscriber environment. And this is very similar to the proxy re-encryption that you might have seen in non-lattice constructions. And the idea is, and there are different flavors, unidirectional, for instance. And the idea is, in the publisher-subscriber, you can change the key under which ciphertext can be decrypted through this process. And this is implemented in PALISADE, but internally it uses the same mechanism as key switching.
Sounds good. So let's thank Yuriy again. And Peter, maybe you can sort of start setting up